Okay, so this is case 3 then. We've got the Euler equation, and we basically end up with case 3 is basically where the two R1 and R2 are both complex numbers. Okay, so let's have a look and see what I mean by that. Well, basically it means that R1 is equal to some real number, lambda, plus I times mu, so some imaginary part, and I2 is equal to lambda, and we've still got the I times mu, but this time we've got a minus instead of a plus, so they're complex conjugates of each other, and that comes about because of the quadratic formula. One of the roots should be positive, one of the roots should be negative. Right, okay, so let's just do a little bit of substitution in this. So x to the power of r, I'm just going to look at the positive root to see what the form of the complex number, what we can do with this. So what's the complex number going to look like? Okay, so I'm just going to sub in x to the power of r1, okay, but you can do exactly the same thing with r2 as well. Okay, so x to the power of r1, I should say, is equal to lambda plus I times mu, yeah? So let's just do a little bit of work with this. This is going to become, I'm just going to split this up now into two, if I'm adding the powers together, I can just split it up into two indices, right? So x to the power of lambda times x to the power of I times mu, yep. Right, okay. So let's have a look at this. So this is now going to become, what's it going to become? This is like, this here, I know how to deal with if I've got an imaginary exponent, if I've got an imaginary power, okay, if it's e to the I theta, okay, I know how to deal with that, I know how to expand that, okay, that is just, what is it, it's cos theta, it's cos theta plus I sine theta, right? I know how to expand that. But at the moment, this here isn't an E. So basically, I need to do something to it to make it into an E. And the idea is, and I showed you this in the last video, so I'm not going to show you the whole ins and outs of it again. So I turn that into an E, then it's just going to be e to the power of ln x. Okay, e to the power of ln x is just x. Okay, nice simple way of showing it. I showed you that in the last video. It's well worth going through and checking that if you're not sure on that. So let's have a look at this. Okay, so now I know how to expand that. If I just let that in there equal my theta, if I just let that equal my theta, then basically I can expand this out. I can say, well, this is going to be, I need a little bit more room than that, so x to the power of lambda times e to the power of I theta effectively. So my theta is just going to be my mu ln x. Okay, so I'll end up with cos of my theta, everything inside my blue bracket there, so mu ln x, okay, plus I sine of my theta, so everything inside my little blue bracket there, so mu ln x, okay, and so that's what I end up with. So when I expand that out, and you can verify that you do exactly the same thing with R2, except with R2, so this is what x to the power of R1 is equal to, x to the R2 is exactly the same thing, x to the R2 is exactly the same thing. Okay, so the next, except instead of a plus being there, there's a minus. That's the only difference. Okay, so sine of mu ln x. Okay, and the reason why I've written that out for you is because I want you to do a job for me. I want you to sub that. I want you to sub that back into the Euler equation. So back into this Euler equation up here. Back into this Euler equation up here to verify that it is actually a solution. Okay, you could do that in your own time, if you so wish, but please, plug it in back into that yourself. You can verify that those are both solutions to the equation. Okay, so in other words, what I'm looking for a general solution of the form y of x is equal to c1 times y1 plus c2 times y2. Well, I can just sub these two things back in. Okay, I can sub these two things back in immediately. So I can sub x to the power of r. I can change this for x to the power of r1. Change this to x to the power of r1 and this to x to the power of the r2. Sub those two things back in, and I end up with my I can verify it is actually a solution. But as you saw with second order differential equations, okay, these two things here have many different solutions. These two things here have many different solutions because you're using cos and sine. You can have many different solutions, right? Okay, now it can be shown that the real part, so in other words, the real part is what? Well, it's x to the power of lambda times cos mu times ln x, okay? The real part is The real part is just that part there, and of course you're being multiplied by x to the power of lambda, okay? So the real part there, and the imaginary part, so the imaginary part is what? Well, the imaginary part is still going to have x to the power of lambda, but it's just going to be times by the bit which has the I with it, right? So x to the power of lambda, and the imaginary part is going to be x to the power of lambda sine of mu times ln x. I should have put that in blue, 1 minute. Sorry, I should have put that in red, so there we go. So I've put that in red now, go away. I've put that in red, okay. And it can actually be shown that these two things are also solutions to your original Euler equation. So in other words, you put those two things back into this Euler equation, they also work. It also comes out as 0, okay. That kind of makes sense because, you know, they're both, you know, these two solutions, these two x to the power of r1 and x to the power of r2, these two solutions, have basically the same except for the plus or the minus. So it makes sense that if you break it down into its smaller parts, that there's still going to be a solution as long as you kind of keep one as the cos part and one as the sine part, then they should still work. Okay, so in other words, what we end up with is if we say, well, this is our first solution, so let's say this is equal to our first solution and this is equal to our second solution. Okay, then basically what we can say is that our general solution, so y of x, is going to be c1 times y1, so c1 times y1, okay, plus c2 times y2, so y1 is equal to x to the power of lambda cos of mu times ln x, okay, and y2 is c2 x to the power of lambda times sine of mu times ln x, okay, and so that's basically the idea. That's basically the idea. Oops, where's that gone? There we go. That's basically the idea there. That's where this kind of long formula came from. It just came from, you know, plugging, you know, working out what the exponents would be. Are they linearly independent? Well, I'll verify, you know, I'll let you verify that for yourself just by working out what the Vronskin is. I'm not going to waste your time with this video. I think I've done enough work with this. I'm sick to death of this at the moment. Because I've just done it for ages. And so basically, you know, I'll let you verify yourself that they are, in fact, linearly independent, that it comes out as non-zero, okay? I think the best way, like the reason why I say I'm sick to death of it is I'm sick to death of all the general terms of it. I think the reason, you know, I think the best thing to do now is to go away and do some examples of Euler equations.